Analysis of algorithm, learning objectives. In this lesson, you will be learning about analysis of algorithm and the following in details. Introduction to algorithm design and data structures, design and analysis of algorithm definition, comparison of algorithms, top-down and bottom-up approaches to algorithm design, analysis of algorithm, frequency count, complexity measures in terms of time and space, structured approach to programming. Introduction. Welcome to the session on analysis of algorithm. This course will help you to understand the data structure concept and how these concepts are useful in problem solving. At the end of the session, you will be able to understand the concepts in object-oriented language such as C++, analyze step-by-step and develop algorithm to solve real-time problems. Introduction to algorithm design and data structures. What this course is about. Data structures and algorithms, ADT, algorithm analysis, programming in C++. Goals of this courses. There are 3 goals. The first is to present the commonly used data structures. The second goal is to introduce the idea of trade-offs and reinforce the concept that there are costs and benefits associated with every data structure. The third goal is to teach how to measure the effectiveness of a data structure or algorithm. Goals of this course. Computer programs should be designed to achieve the following goals. To design an algorithm that is easy to understand, code and debug. To design an algorithm that makes efficient use of computers' resources. Need for data structures. A solution is said to be efficient if it solves the problem within the required resource constraints. Need to utilize the hardware effectively. Easy to do operations such as insertion, deletion, update, researching. When selecting a data structure to solve a problem, you should follow these steps. Analyze your problem to determine the basic operations that must be supported. Examples of basic operations include inserting a data item into the data structure, deleting a data item from the data structure, and finding a specified data item. Quantify the resource constraints for each operation. Select the data structure that best meets these requirements. Ask yourself whenever you must choose a data structure, are all data items inserted into the data structure at the beginning, or are insertions interspersed with other operations? Static applications, where the data are loaded at the beginning and never change, typically require only simpler data structures to get an efficient implementation than dynamic applications. Can data items be deleted? If so, this will probably make the implementation more complicated. Are all data items processed in some well-defined order, or is search for specified data items allowed? Random access search generally requires more complex data structures. Structure. How data is organized. Place data contiguously. Place data here and there with links. Place data with formula. ADT. An abstract data type, ADT, is a mathematical model for a certain class of data structures that have similar behavior, or for certain data types of one or more programming languages that have similar semantics. An abstract model of a data structure together with the operations can be treated as a form of algorithm processed on the data structure. In C++ or Java, an ADT can be implemented as a class. The relationship between data items abstract data types and data structures. The ADT defines the logical form of the data type. The data structure implements the physical form of the data type. Design and analysis of algorithms. Algorithm's definition. An algorithm is a method or a process followed to solve a problem. Design, analyze, implement, experiment. Advantages of algorithm. Solve a big problem in a simple way. It is a step-by-step process so that it would be understandable. Every algorithm is best in any one of the situation. Modification is simple based on the situation. Algorithm properties. It must compute the desired function, converting each input to the correct output. Note that every algorithm implements some function because every algorithm maps every input to some output. An issue here is whether a given algorithm implements the intended function. Concrete means that the action described by that step is completely understood and doable by the person or machine that must perform the algorithm. Each step must also be able in a finite amount of time. The algorithm gives us a recipe for solving the problem by performing a series of steps, where each such step is within our capacity to perform. The ability to perform a step can depend on who or what is intended to execute the recipe. For example, the steps of a cookie recipe in a cookbook might be considered sufficiently concrete for instructing a human cook, but not for programming an automated cookie-making factory. Often, it is the next step of the algorithm description. Selection is normally a part of any language for describing algorithms. Example, the if statement in C++. Selection allows a choice for which step will be performed next, but the selection process is unambiguous at the time when the choice is made. If the description for the algorithm were made up of an infinite number of steps, we could never hope to write it down nor implement it as a computer program. Most languages for describing provide some way to perform repeated actions known as iteration. Examples of iteration in programming languages include the while and for loop constructs of C++. Iteration allows for short descriptions with the number of steps actually performed controlled by the input. If an algorithm contains any loop, it means it should terminate. It may not go into an infinite loop. No closed loop should be allowed. This property is used to avoid the deadlock. Algorithm analysis. A process of determining the amount of time, resource, etc. required when executing an algorithm. Big O notation. Big O notation is used to capture the most dominant term in a function and to represent the growth rate, also called asymptotic upper bound. Example, 100n to the power of 3 plus 30,000 n equals greater than O of n to the power of 3. 100n to the power of 3 plus 2n to the power of 5 plus 30,000 n equal to greater than O of n to the power of 5. Functions in order of increasing growth rate. The table shows the functions in increasing order of growth rate. If the result would be C, then it would be called as constant. Same value for each iteration. The next rate is log n, where n is the number of steps followed by the algorithm. The next iteration is log square n. It is a medium rate. Next is n, called as n steps followed by the algorithm. N log n worse than the n. The worst algorithm will contain n cube and second cases. Examples of algorithm running times. Minimum element in an array, O of n. Closest points in the plane, that is, smallest distance pairs. N of n minus 1 divided by 2 equal to greater than O of n square. Collinear points in the plane, that is, 3 points on a straight line. N of n minus 1 of n minus 2 divided by 6 equals to greater than O of n cube. Brute force algorithm, O of n cube. Brute force is a crude algorithm which works through every possible answer until the correct one is found. Some problems can be solved this way, but others, for instance, obtaining the prime factors of large numbers or picking the best chess move, have far too many possibilities to be solved that way, except in simple cases. We do not need precise calculations for a big O estimate. In many cases, we can use the simple rule of multiplying the size of all the nested loops. O of n square algorithm. If we have already calculated the sum for the subsequence I to j minus 1, then we need only one more addition to get the sum for the subsequence I to j. However, the cubic algorithm throws away this information. If we use this observation, we obtain an improved algorithm with a running time O of n square. O of n algorithm. O of n is the average case in the time complexity. If we use this observation, we obtain an improved algorithm with the running time O of n. Here, this algorithm provides the sample for O of n case, where every loop iterates only n times. General big O rules are listed below. Mathematical expression related to rate of growth. The table shows the relationship between mathematical expression and rate of growth. T is called as big O. F is called as function. If T of n equals to O of f of n, then the growth is equal. As same like this, the table denotes for each cases. Various growth rates. The result shows the rate between the mathematical and functional relationship. If T of n is equal to O of 1, then it should be constant. Like while the slide shows the results for every cases in time complexity. Worst case versus average case. This slide represents the average and worst case difference. As said before, O of n is the average case for a specified algorithm. More than O of n are called as worst case. In sometimes, the average case will be a best case depending upon the situation. Therefore, the worst case is considered as average case. Static searching problem. Given an integer x and an array A, return the position of x in A or an indication that it is not present. If x occurs more than once, return any occurrence. The array A is never altered. Sequential search equal to greater than O of n. Binary search sorted data equal to greater than O of log n. Interpolation search data must be uniformly distributed, making guesses and search equal to greater than O of n in worst case, but better than binary search on average big O performance. Impractical in general. Sequential search. A sequential search steps through the data sequentially until a match is found. A sequential search is useful when the array is not sorted. A sequential search is linear O of n, that is, proportional to the size of input. unsuccessful search n times, successful search worst n times, successful search average n by 2 times. Binary search. If the array has been sorted, we can use binary search, which is performed from the middle of the array rather than the end. We keep track of low end and high end, which delimit the portion of the array in which an item, if present, must reside. If low end is larger than high end, we know the item is not present. Binary search three-way comparisons. The example shows a three-way comparison of binary searching. In this, it would be compared by using if conditions. 3 if conditions will get 3 different ways of complicity. Here, the if of A mid lesser than X will get lower. The next else if will get average, and the last else will get higher case. Binary search is logarithmic O of log n because the search range is half in each iteration. Binary search two-way comparison. The code shows the two-way comparison. Two-way comparison's binary search is still O of log n. This is effective than the three-way comparison. The program is about comparing two numbers. Limitations of big O analysis. The constant's coefficients might have a significant influence on the performance when the size of the problem is not large. Example, f of n equals to 2n log n versus g of n equals to 1000n. Which is faster? It depends on n. For little n, f of n is better, although its growth rate is larger. Worst case is sometimes uncommon and can be safely ignored. At other times, it is very common and cannot be ignored. Average case analysis is almost always much more difficult than worst case analysis. Statistics, function calls. The statistics between normal programming and dynamic programming show by using the function call. The result is dynamic programming is effective than the normal programming. Dynamic programming. Divide and conquer, a top-down approach. Many smaller instances are computed more than once. Dynamic programming, a bottom-up approach. Solutions for smaller instances are stored in a table for later use. An algorithm design technique, a framework to solve optimization problems, elements of dynamic programming. Dynamic programming version of a recursive algorithm. Developing a dynamic programming algorithm. Example, multiplying a sequence of matrices. It sometimes happens that the natural way of dividing an instance suggested by the structure of the problem leads us to consider several overlapping sub-instances. If we solve each of these independently, they will in turn create a large number of identical sub-instances. If we pay no attention to this duplication, it is likely that we will end up with an inefficient algorithm. If on the other hand we take advantage of the duplication and solve each sub-instance only once, saving the solution for later use, then a more efficient algorithm will result. The underlying idea of dynamic programming is thus quite simple. Avoid calculating the same thing twice, usually by keeping a table of known results which we will fill up as sub-instances are solved. Dynamic programming is a general algorithm design technique, invented by American mathematician Richard Bellman in the 1950s to solve optimization problems. Programming here means planning. Main idea: solve several smaller overlapping sub-problems. Record solutions in a table so that each sub-problem is only solved once. Final state of the table will be or contain the solution. Define a container to store intermediate results. Access container versus recomputing results. Fibonacci numbers example, top-down. Use vector to store results as calculated so that they are not recalculated. Recall definition of Fibonacci numbers. F of n is equal to f of n minus 1 plus f of n minus 2 for n is greater than or equal to 2. Computing the nth Fibonacci number recursively, top-down. Dynamic programming. Fibonacci versus Fibonacci dynamic. The program shows detailed view of normal algorithm and dynamic algorithm. The output computes the difference. Recursive calls for Fibonacci. The output diagram shows the Fibonacci series in recursive call. Fibonacci using dynamic programming. The output diagram shows the Fibonacci series in dynamic programming. Top-down versus bottom-up. Top-down dynamic programming moves through the recursive process and stores results as algorithm computes. Bottom-up dynamic programming evaluates by computing all functional values in order, starting at lowest and using previously computed values. Examples of dynamic programming algorithms. These are some of the dynamic programming algorithms: computing binomial coefficients, optimal chain matrix multiplication, Floyd's algorithms for all pairs shortest paths, constructing an optimal binary search tree, some instances of difficult discrete optimization problems, traveling salesman, knapsack. A framework to solve optimization problems. A framework to solve optimization problem. Need sub-problems form a big problem. Determine the cost. Select the choice that produce the minimum cost. Elements of dynamic programming. Constructing solution to a problem by building it up dynamically from solutions to smaller or simpler sub-problems. Sub-instances are combined to obtain sub-instances of increasing size until finally arriving at the solution of the original instance. Make a choice at each step, but the choice may depend on the solutions to sub-problems. Principle of optimality. The optimal solution to any problem is a combination of optimal solution. Memorization for overlapping sub-problems. Development of a dynamic programming algorithm. How to develop the dynamic programming. Characterize the structure of an optimal solution. Breaking a problem into sub-problem. Whether principle of optimality apply. Recursively define the value of an optimal solution. Define the value of an optimal solution based on value of solutions to sub-problems. Compute the value of an optimal solution in a bottom-up fashion. Compute in a bottom-up fashion and save the values along the way. Later steps use the save values of previous steps. Construct an optimal solution from computed information. Binomial formula. Binomial coefficient. Cannot compute using this formula because of n. Binomial using divide and conquer. Binomial using dynamic programming. Just like Fibonacci, that formula is very inefficient. Instead, we can use the following. Bottom-up. Recursive property. Frequency count. Counting each code. Loop counting. For each instruction, predict how many times each will be encountered as the code runs. The FC, frequency count, n, is the term used for counting. Order of magnitude. By itself, frequent count is relatively meaningless. Order of magnitude. Estimate of performance versus amount of data. To convert f.c to order of magnitude, discard constant terms, disregard coefficients, pick the most significant term. Worst case path through algorithm. Order of magnitude will be big O, that is, O of n. Another example. Discarding constant terms produces 3n square plus 2n. Clearing coefficients, n square plus n. Picking the most significant term, n square. Space complexity. Space efficient as possible and develop schemes to make memory appear larger than it really was, virtual memory and memory paging schemes. Handheld computer-based equipment like cell phone, palm devices, etc. Space complexity is the amount of memory required by an algorithm to run to completion. Core dumps equals the most often encountered cause is memory leaks. The amount of memory required larger than the memory available on a given system. Some algorithms may be more efficient if data completely loaded into memory. To look also at system limitations. Example, classify 2 GB of text in various categories: politics, tourism, sport, natural disasters, etc. Can I afford to load the entire collection? Fixed part. The size required to store certain data or variables that is independent of the size of the problem. Example, name of the data collection, same size for classifying 2 GB or 1 MB of text. Variable part. Space needed by variables whose size is dependent on the size of the problem. Example, actual text. Load 2 GB of text versus load 1 MB of text. S of P equals C plus S of instance characteristics. C equals constant. Complexity measures in terms of time and space. To find out the efficiency of an algorithm, we need to examine the space and time complexity. The space is about memory. The time is about number of instructions. Time complexity. Is the algorithm fast enough for my needs? How much longer will the algorithm take if I increase the amount of data it must process? Given a set of algorithms that accomplish the same thing, which is the right one to choose? Constant time. Constant time effectively means you can give a constant upper bound to how much the program will take to run, which isn't affected by any of the input parameters. Compare that with, say, linear time for some input n, which will often actually be the size of the input data rather than a direct value, which means that the upper bound of the time taken can be expressed as mn plus k for some values of m and k. Here are some examples of code fragments that run in constant time. Logarithmic time. The most common attributes of logarithmic running time function are that the choice of the next element on which to perform some action is one of several possibilities, and only one will need to be chosen. Or the elements on which the action is performed are digits of n. Polylog arithmetic time. An algorithm is said to run in polylog arithmetic time if t of n equals O of log n of k for some constant k. For example, matrix chain ordering can be solved in polylog arithmetic time on a parallel random access machine. Sublinear time. If t of n equals O of n means it is set to be sublinear time. Typical algorithms that are exact and yet run in sublinear time use parallel processing or alternatively have guaranteed assumptions on the input structure. Sublinear time algorithms are typically randomized and provide only approximate solutions. In fact, the property of a binary string having only zeros can be easily proved not to be decidable by a sublinear time algorithm. Sublinear time algorithms arise naturally in the investigation of property testing. Linear time. If time complexity is O of n, it means it is linear time. Most of the case, the biggest input size running on O of n. Examples are Boyer-Moore algorithm and Yukonon's algorithm. Linear arithmetic time. If T of n is O of n, it means it is linear arithmetic time. Some famous algorithms that run in linear arithmetic time include quick sort in the average case, heap sort, merge sort, intro sort, binary tree sort, smooth sort, patient sorting, etc. in the worst case. Fast Fourier transforms, Monge array calculation. Quasi-linear time. A generalization of linear arithmetic time is quasi-linear time. An algorithm is said to run in quasi-linear time if T of n equals O of n log to the power of km for any constant k. Linear arithmetic time is the case k equals 1. Quasi-linear time algorithms are also O of n1 and thus run faster than any polynomial in which n with the exponent strictly is greater than 1. Sub-quadratic time. An algorithm is said to be sub-quadratic time if T of n equals O of n square. Example, insertion sort, shell sort. Polynomial time. An algorithm is said to be of polynomial time if its running time is upper bounded by a polynomial expression in the size of the input for the algorithm. That is, T of n equals O of n to the power of k for some constant k. Some examples of polynomial time algorithms. The quick sort sorting algorithm on n integers performs at most a(n) square operations for some constant a. Thus, it runs in time O of n square and is polynomial time algorithm. All the basic arithmetic operations, addition, subtraction, multiplication, division, and comparison can be done in polynomial time. Maximum matching in graphs can be found in polynomial time. Strong and weak polynomial time. These two concepts are only relevant if the inputs to the algorithm consist of integers. Strong polynomial time is defined in the arithmetic model of computation. In this model of computation, the basic arithmetic operations, addition, subtraction, multiplication, division, and comparison, take a unit time step to perform, regardless of the sizes of the operands. The algorithm runs in strong polynomial time if the number of operations in the arithmetic model of computation is bounded by a polynomial in the number of integers in the input instance, and the space used by the algorithm is bounded by a polynomial in the size of the input. Complexity classes. P. The complexity class of decision problems that can be solved on a deterministic Turing machine in polynomial time. NP. The complexity class of decision problems that can be solved on a non-deterministic Turing machine in polynomial time. ZPP. The complexity class of decision problems that can be solved with zero error on a probabilistic Turing machine in polynomial time. RP. The complexity class of decision problems that can be solved with one-sided error on probabilistic Turing machine in polynomial time. BPP. The complexity class of decision problems that can be solved with two-sided error on a probabilistic Turing machine in polynomial time. BQP. The complexity class of decision problems that can be solved with two-sided error on a quantum Turing machine in polynomial time. Superpolynomial time. An algorithm is said to take superpolynomial time if t of n is not bounded above by any polynomial. It is omega of n to the power of c time for all constants c, where n is the input parameter, typically the number of bits in the input. For example, an algorithm that runs for 2n steps on an input of size n requires superpolynomial time. An algorithm that uses exponential resources is clearly superpolynomial, but some algorithms are only very weak superpolynomial. For example, the Adleman-Pomerantz-Rumeli primality test runs for n to the power of O log n time on n-bit inputs. This grows faster than any polynomial for large enough n, but the input size must become impractically large before it cannot be dominated by a polynomial with small degree. An algorithm that requires superpolynomial time lies outside the complexity class P. Cobham's thesis posts that these algorithms are impractical, and in many cases they are. Since the P versus NP problem is unresolved, no algorithm for an NP complete problem is currently known to run in polynomial time. Quasi-polynomial time. Quasi-polynomial time algorithms are algorithms which run slower than polynomial time, yet not so slow as to be exponential time. The worst case running time of a quasi-polynomial time algorithm is 2 to the power of O of log n to the power of c for some fixed c. The best known classical algorithm for integer factorization, the general number field sieve, which runs in time about 2 to the power of O to the power of n 1/3, is not quasi-polynomial since the running time cannot be expressed as 2 to the power of O to the power of log n to the power of c for some fixed c. If the constant c is the definition of a quasi-polynomial time algorithm is equal to 1, we get a polynomial time algorithm, and if it is less than 1, we get a sublinear time algorithm. Quasi-polynomial time algorithms typically arise in reductions from an NP hard problem to another problem. For example, one can take an instance of an NP hard problem, say 3 SAT, and convert it to an instance of another problem B. But the size of the instance becomes the complexity class QP and consists of all problems which have quasi-polynomial time algorithms. It can be defined in terms of D time as follows. Relation to NP complete problems. In complexity theory, the unsolved P versus NP problem asks if all problems in NP have polynomial time algorithms. All the best known algorithms for NP complete problems like 3SAT, etc. take exponential time. Indeed, it is conjectured for many natural NP complete problems that they do not have sub-exponential time algorithms. Here, sub-exponential time is taken to mean the second definition presented above. This conjecture for the K-SAT problem is known as the exponential time hypothesis. Since it is conjectured that NP complete problems do not have quasi-polynomial time algorithms, some inapproximability results in the field of approximation algorithms make the assumption that NP complete problems do not have Quasi-polynomial time algorithms. Sub-exponential time. The term sub-exponential time is used to express that the running time of some algorithm may go faster than polynomial, but it is significantly smaller than an exponential. First definition. A problem is said to be sub-exponential time solvable if it can be solved in running times whose logarithms grow smaller than any given polynomial. More precisely, a problem is in sub-exponential time if for every epsilon greater than 0, there exists an algorithm which solves the problem in time O of 2n epsilon. The set of all such problems is the complexity class sub-exponential, which can be defined in terms of d time. Second definition. This definition allows larger running times than the first definition of sub-exponential time. An example of such a sub-exponential time algorithm is the best-known classical algorithm for integer factorization, the general number field sieve, which runs in time about 2 to the power of O to the power of n 1/3, where the length of the input is n. Note that it makes a difference whether the algorithm is allowed to be sub-exponential in the size of the instance, the number of vertices, or the number of edges. In parameterized complexity, this difference is made explicit by considering pairs. Exponential time hypothesis. The exponential time hypothesis, ETH, is that 3-SAT, the satisfiability problem of Boolean formulas in conjunctive normal form with at most 3 literals per clause and with n variables, cannot be solved in time 2 to the power of O to the power of n. The exponential time hypothesis implies P not equal to NP. Exponential time. An algorithm is said to be exponential time if T of n is upper bounded by 2 to the power of poly of n, where poly of n is some polynomial in n. Sometimes exponential time is used to refer to algorithms that have T of n equals 2 to the power of O of n, where the exponent is at most a linear function of n. This gives rise to the complexity class E. Double exponential time. An algorithm is said to be double exponential time if T of n is upper bounded by 2 to the power of 2 poly of n, where poly of n is some polynomial in n. Such algorithms belong to the complexity class 2exp time. Structured programming. Structured programming is a programming paradigm aimed at improving the clarity, quality, and development time of a computer program by making extensive use of subroutines, block structures, and for and while loops, in contrast to using simple tests and jumps such as the go-to statement, which could lead to spaghetti code, which is both difficult to follow and to maintain. Low-level structured programming. At a low level, structured programs are often composed of simple, hierarchical program flow structures. These are sequence, selection, and repetition. The all flow are if, while, do, while, begin, and etc. Sequence refers to an ordered execution of statements. In selection, one of a number of statements is executed depending on the state of the program. This is usually expressed with keywords such as if then else, end if, switch, or case. In some languages, keywords cannot be written verbatim but must be stopped. In repetition, a statement is executed until the program reaches a certain state or operation have been applied to every element of a collection. This is usually expressed with keywords such as while, repeat, for, or do, until. Often it is recommended that each loop should only have one entry point. Common deviations. The most common deviation found in many languages is the use of a return statement for early exit from a subroutine. The structured languages are commonly used if, then, else, while, and for. This results in multiple exit points instead of the single exit point required by structured programming. Structured programming languages. Some of the languages initially used for structured programming languages include ALGOL, Pascal, PLI, and ADA. But most new procedural programming languages since that time have included features to encourage structured programming. Outcome. By the end of the 20th century, nearly all computer scientists were convinced that it is useful to learn and apply the concepts of structured programming. High-level programming languages that originally lacked programming structures, such as Fortran, COBOL, and BASIC, now have them. Early exit. At the level of functions, this is a return statement. At the level of loops, this is a break statement or continue statement. Terminate the loop. Terminate the current iteration, proceed with next iteration. C language. C is an early and prominent example of these constructs. Multiple exits can arise for a variety of reasons. If returning a value, it has completed the calculation. Example, a trace statement. For instance, in later development, a return statement could be overlooked by a developer, and an action which should have been performed at the end of a subroutine might not be performed in all cases. Exception handling. A typical example of a simple procedure would be reading data from a file and processing it. Conclusion. Thus we learned about analysis of algorithm and the following in details. Introduction to algorithm design and data structures, design and analysis of algorithm definition, comparison of algorithms, top-down and bottom-up approaches to algorithm design, analysis of algorithm, frequency count, complexity measures in terms of time and space, structured approach to programming.